Hi, everyone. Today we're going to talk about relative growth rates. But before we get to that, let's take a look at the opener. We're going to do a little bit of review of what we were talking about last time. So, limit as x approaches infinity of root x over natural log of x. So, if I try to plug in a really large number into both of these, they're both going to infinity, which means this is giving us an indeterminate form, right? Which means we have to use L'Hopital's rule. I like to write LHOP for short. So let's go ahead and take the derivative of each of these. So limit as x approaches infinity. Whoops, sorry, wrong tool there. Let's go ahead and take their derivative. So derivative of root x is 1 over 2 root x. Derivative of the natural log of x function is 1 over x. We can go ahead and rewrite this. And we get x over 2 root x, but we can take the x and the 2 root x here, right? Root x is just x to the 1/2. So we can actually go ahead and divide this a little bit more, right? And so we just get root x in the numerator over 2. And as this goes to infinity, right, this is just going to be infinite. Okay. Okay, let's take a look at b. Now, natural log of x over natural log of x squared. If I apply the same logic to the last one, right, natural log of x is infinite as x goes to infinity. If I square that number, it's still infinite. So this is infinity over infinity, another indeterminate form. I should use L'Hopital's rule, right? Wrong. Okay. And one of the things I notice after teaching students L'Hopital's rule is every time they get a limit, they just go, oh yeah, this must be a L'Hopital's rule question. That could not be further from the case, right? So just one thing we have to keep in mind, right? You did lots of limits in Calc A, right? There's lots of strategies you can use when evaluating a limit. L'Hopital's rule is not always necessary, okay? So what should I do instead here? Well, if I take a look at my denominator, I can apply a little bit of an exponent property, right? Guys, I have this squared, right, with inside of my natural log. And so I can go ahead and take that out, and I get 2 times natural log of x, which will cancel out with the natural log of x in the numerator, meaning this whole thing is just 1/2, no L'Hopital's rule necessary. Okay? All right. So let's get to the lesson. So we're talking about relative growth rates, and you'll notice it says revisited here because this is actually going to be going along with something you did back in Calculus A as well, which is the hierarchy of functions. So I actually want us to jump down to the last page of the notes here. Okay. Relative rates of growth of common function families. All right. So I like to call this the hierarchy of functions, right? So in other words, think of this like a race. Okay. As x goes to infinity, you can think of your x-axis as kind of like time in this context, right? Which functions are winning the race, right? We, think of it like a marathon, right? We know everyone will finish the marathon. Well, hopefully everyone will finish the marathon, but we know some runners are going to finish it in, 2 hours and 30 minutes, and some will finish it in 6 hours, right? So, the goal here is to try to figure out which ones are slowest to fastest, right? This is calculus. We talk about derivatives. We talk about slopes, right? Instantaneous rate of change, all of that goes along with like velocity, right? So we kind of understand this idea of like, okay, the steeper the curve, the faster it's growing. That's what we're talking about here, okay? So if we rank these, right, you'll notice that one of these is kind of an oddball function, which is 1 over x. The reason it's an oddball is because as x goes to infinity, 1 over x, the reciprocal function, goes to 0, right? So this function is not finishing the marathon, okay? So what grows faster than that, right? The logarithmic function, right? Log of x base a. Remember, natural log of x is a subset of that, okay? Okay, then we have the square root function, so that is faster than the log function, right? Radicals. Okay, then we have the linear function, right? So x to the first power. And then we have just polynomials in general, right? X to the a. And so, x cubed is faster than x squared. X to the fourth is faster than x cubed, etc. Okay, then we have the exponential functions, right? So 2 to the x, right? E to the x is faster than 2 to the x. 3 to the x is faster than e to the x, right? Those are all exponential, okay? Then we have the factorial function is faster than that, and then the fastest function, right, is the one without a name, right? Variable to a variable, x to the x, or anything like that, okay? Okay, so hopefully this is all looking familiar, right? Hopefully this is some Calc A review. Now, let's go back to the first page and let's revisit these, okay? So limit as x grows to infinity of f of x over g of x in front of all of these, right? So what is that limit going to equal when f of x grows faster than g of x? So when the numerator is a faster growing function than the denominator, right? It is going to be infinity. When f of x is slower than g of x, meaning the denominator is faster, that limit is 0. And when f of x and g of x grow at the same rate, right, this is where you get any type of constant answer, okay? Okay, so let's look at some examples of these kinds of questions, okay? So group problem 1, which grows faster, e to the x or 100x squared? Now, a lot of you should be able to look at this, right? Look at what we did on the first page, look at what we did with the hierarchy, and be able to come up with an answer without having to do any work. Okay, our goal, and to tie this in with our L'Hopital's rule work, is to basically do a little proof. Okay, right? Instead of just saying, okay, I've memorized the hierarchy of functions, how could I prove which function grows faster, right? And so let's go ahead and treat this like a proof. Let's do some work. As x goes to infinity, right, both of these are growing infinitely larger, right? So infinity over infinity is my indeterminate form. So it's L-hop time, right? And so let's go ahead and take the derivative. And so I get e to the x over 200x, okay? And again, both of these are growing ever larger, and that means I can do L'Hopital's rule again. And so if I do it one more time, I get e to the x over 200. And now these are not both growing infinitely, right? 200 is a constant, e to the x in the numerator, definitely faster. And so this is infinite, right? Which means that f of x is the faster growing function because that was my numerator. Okay. Okay. Let's take a look at B, right? This one not as straightforward as the last one with the hierarchy. Root x minus 5 over root 5x plus 1. Now, I'm just saying the functions. Don't forget, I am looking to see that you are writing limit as x approaches whatever value or infinity in front of every line of your work until you evaluate that limit, okay? So the first thing I would say to do for this one is we have 2 square roots. Let's go ahead and write this as 1 square root. Okay, so limit as x approaches infinity, big square root x minus 5 over 5x plus 1. Now, what are we going to do with that? Well, remember that a square root is basically just an exponent, right? So instead of writing a big square root, I could say the whole thing is to the 1/2 power, right? And the reason why I want to do that is because there is a limit property you might recall from Calculus A that says that if you have an exponent in your limit, you can actually take the limit of what is inside and then apply that exponent. So that's a fancy way of saying I can take that square root and put it around the entire limit itself. So I can do the limit and then just take the square root of that. And so now this is a very nice limit, right? Because this is x minus 5 over 5x plus 1. X is going to infinity. Ignore the minus 5. Ignore the plus 1. X over 5x. And so that is just going to give me 1/5, right? And now that whole thing is inside the square root, okay? Now, the goal here is not really to figure out what the limit value is in a nice, concise answer. The goal is to say which is the faster growing function, right? And in this case, the square root of 1/5 qualifies as any constant, right? So I don't need to worry about rationalizing or any of that, right? This is good enough for my proof. And so I can say safely that f of x and g of x grow at the same rate. Okay. Okay. Example 1. some odd looking functions here. Square root of 3 to the x minus 2 to the x, and then g of x is 10 to the 4x power. Okay, so when you get something like this, and this is a very common type of question for this subject matter, right? When you have one of the functions has like a radical and the other one doesn't, right? The strategy here is just give them both a radical. So in other words, this is a square root in my numerator. How could I write the denominator as the square root of something so that it would be equal to this, right? Well, if I square this, meaning take it to the second power, right? Exponent to the next exponent, that would be 10 to the 8x. If I were to take the square root of that, it would give me 10 to the 4x, okay? And now I have square root over square root. So let's apply the same strategies as the last question, right? And we don't have to do that middle step of putting a square root around the whole fraction. Let's just do the square root around the whole limit, okay? And now, why would I want to do it around the whole limit? Well, now what I can do is I can split this up into two separate fractions and two separate limits. So I have a really big square root now as x goes to infinity, or sorry, limit as x goes to infinity of 3 to the x over 10 to the 8x minus limit as x goes to infinity 2 to the x over 10 to the 8x. That whole thing is in a big square root, okay? And why would I want to split it up like this? Well, because now I have two things that can be written as raised to the x power. And so I can go ahead and rewrite this, right, as limit as x goes to infinity. This is 3 over 10 to the 8th power, right, because 8x is a product. And so that's exponent to the exponent. So 10 to the 8th to the x power is equal to what I have there, right? And then same thing with my other fraction. Okay, and now we can kind of just remember some properties of exponential functions. 3 over 10 to the 8th is definitely less than 1, right? And so this is actually like exponential decay with this. And so this is going to 0, and so is the second one. And so this whole thing becomes the square root of 0 minus 0, which is 0. Okay, and when I get 0, right, that means my denominator function, right, my g of x, 10 to the 4x, that was the faster growing function. Okay, so this one, you know, a lot of work here just to kind of split it up and rewrite it into ways that we already know, but it works out nicely. Okay, and the thing I'll give you a little hint on, you know, for the future is that with a lot of these questions, you're gonna probably know the answer before you start going into your work. Okay, which is very common with this, which is fine, right? I want you to have that knowledge. Now you just got to prove it. Okay. Okay, example 2, let's keep going. Okay, so f of x is x squared. G of x is something to the 1/3 power. Well, remember, something to the 1/3 power just means that it's the cube root, right? And so with my numerator, I'm going to just rewrite x squared as x to the 6th inside of a cube root. Now they're both in a cube root, right? So let's go ahead, right, do one fraction here, and then with one square root, let's do, cube root. Let's do cube root around the whole limit. And to be honest, if I was writing this again, I probably would have skipped this step, right? I probably would have just gone from there to there. I think that's fine, okay? And so inside of this now, I have x to the 6th over x to the 6th, right? I can ignore the plus 5 as I go to infinity. And so that whole limit is just 1. And so this becomes the cube root of 1, which is 1, right? And so I get any type of constant here, which tells me that these functions are growing at the same rate. Okay. Okay, let's keep going. Okay, now, example 3, we kind of switch things up here a little bit. Okay, f of x is x to the x. G of x is e to the x. Okay, now, you got to be careful here, okay? When I have like multiple exponential ones, and specifically with part A, it's again from like the last video as well, you get this variable to a variable thing going on. You're gonna want to involve natural log in your work, okay? Because you got that log property. And so what I'm going to do instead is I'm going to compare these two functions. A of x is the natural log of f of x. B of x is the natural log of g of x, okay? And whatever I get for this will actually apply for f and g as well, okay? So limit as x approaches infinity of a of x over b of x. So let's go ahead and plug in my functions. Natural log x to the x over natural log of e to the x. Let's go ahead and apply our log property 2 times. The x's come out in front of both of those, which is great because they will cancel, right? And now, what is natural log of e? Natural log of e is just 1. And so I get natural log of x over 1, which is just natural log of x. And we know that function is going to infinity, right? And so we know that f of x is the faster growing function. Again, you're going to see questions like this where if you just remember your hierarchy of functions, you know x to the x is faster than e to the x, right? But you still got to be able to prove it. Okay. Now, a student a couple of years ago brought up, hey, isn't there a much simpler way of doing this? Yes, there is, right? Another way of approaching this one is you can say that, hey, these are both just exponential functions, so no natural log of whatever, right? You can just rewrite it just like how we did on example 1 here, right? Where we took our 2 exponentials and rewrote it as 1 base to the x power, right? We did that 2 times. We can do that here as well. This becomes x over e to the x power, right? And so that's just, the e is just a coefficient, right? That doesn't really matter. It's still x to the x, right? Basically, and so we know that's infinity, and so we know f of x is faster. So that's a little shorter proof, but this natural log stuff, whenever you have like variable to a variable, is very important. Okay, now our last question, part B, I changed this from whatever the question originally said. So let's change it up. Okay, f of x is just x, g of x is x squared. Now again, you all know what's the faster function between these two. The reason why I wanted to change it to these 2 functions is because I want to show you how taking the natural log of your function is only useful when you have variable in the exponent, okay? If you apply the logic from part A into part B, you're going to get something very bad, right? Now, let's spoil the answer here. We all know x squared grows faster than x, right? We know g of x should be faster. But if I do the work and I say, okay, natural log of x squared, limit as x approaches infinity of a of x over b of x, I apply the log property, right? Natural log of x is cancel. I get 1/2, x and x squared grow at the same rate because I got a constant? We know that's not true, okay? So again, this strategy of I'm going to take the natural log of each of my functions only applies when I have a variable in the exponent. You can't just do it for any functions willy-nilly, okay? So x over x squared, right? Let's do this the right way, again, even though we know the answer, right? And now this is a straight up calculus A question, right? Simplify, we get 0, right? G of x is faster. We knew that without even doing this, okay? Okay, a lot of proofs today though, okay? So, this is something you're gonna get asked to do on a test. The nice thing is on the AP test, these types of questions are typically just multiple choice, right? So, there's not a lot of work required, but again, for your response, you got to be ready, okay? All right, we'll leave it with that, and I'll see you guys next time.